We might not notice, but tremendous technology and mind-boggling science constantly surround us in the products we use every day. Behind their practical use lurk hidden histories, dramatic discoveries, and awesome experiments. They are wicked inventions. Coming up, motorbikes. We reveal the hand-built perfection behind this road racer. Nuclear power. We find out how a submarine can stay underwater for 25 years. Ski boots. From work boots and strings to the high-tech footwear of today, we explain the science behind the ski boot. We reveal the surprising science and amazing manufacture behind these wicked inventions. Motorcycles are now made for a range of different purposes, such as commuting, racing, and off-road fun. But just how were they first introduced?
So one of the key pointers when you're thinking about the history of the motorcycle is the word cycle. In the 19th century, French bike manufacturers started to play around with the idea of putting little gas propulsion turbine engines on the back of bikes, so we'd actually drive the mechanisms. So you got these wonderful little kind of like gas steam powered almost bicycles, which became really popular in France. But it was actually a little bit later in that century, in the 1890s, when a German company called Hilderbrand and Wolfmüller took the concept of the kind of French cycle with the gas propulsion on the end and put the combustion engine in it.
The Hilderbrand and Wolfmüller bike was the first mass-produced motorcycle in the world. However, there were only several hundred units produced, which meant that many other motorcycle makers started building their designs around the world and found opportunities to sell more. Other than this alternative engine design, there were little changes in the use and purpose of the motorcycle until 1914, during the First World War.
It was really in the First World War when you started to see a real usage, practical usage for motorbikes. Obviously, they can go places cars can't go, they're fast, they're cheap to run.
Even during and after the Second World War, bikes were still used to deliver messages by dispatch riders, who would brave battlefield and busy roads to pass messages from one person to another.
So you have this kind of cultural thing, you have the needs of the working people to have an easy system of transportation. Companies can make motorbikes cheaply, they're cheap to run, they're fuel efficient, and like I said before, they can get into places other cars, other vehicles can't really do.
Motorbikes really are wicked inventions, but just how are they made? Norton motorcycles have a rich history in motorcycle manufacturing. The brand is synonymous with handmade bikes capable of winning the biggest of competitions.
Norton, the brand, was formed in 1898 by James Lansdowne Norton in Birmingham. And then in 2008, I purchased the brand and we built and delivered our first bike in May 2010. When we got Norton back and we got it back into Britain, was to look at the past history and the past glory from Norton, from its heyday and its glory years. People just kind of have a Norton story, as their dad had one or their granddad had one. That's one of the tricks of making sure Norton is fit and healthy, is making sure we stay connected with history, but wholly current in the 21st century, and have a motorcycle that excites and brings that passion back into our customers today.
The production of one of their motorcycles begins with product design, where designers will craft their ideas using computer-aided design software, better known as CAD. Once the designs are complete, it's time for the physical work to begin. All Norton motorcycles start life in the fabrication shop, where formed steel parts are hand-welded to craft the frame of the bike.
Well, our fabrication shop is a bit of a jewel in the crown, really, because it's a really exciting place. Bits of straight metal go in and motorbike frames come out. We do all sorts of different welding, TIG welding and MIG welding, but also hand fabricating high-end race bike frames to go around the TT at 200 miles an hour.
Using a purpose-built jig, the engineers are able to fix all of the separate metal components together, ready to be tacked into place. Tacking is a welding process that essentially fixes the metal in position, ready to receive its final weld. It takes around 8 hours to build a frame like this, so concentration and precision is vital. As well as the frame, other metal parts of the motorcycle are also built and hand-welded, such as the fuel tank. The weld on this tank needs to be absolutely perfect, as it will be part of the finished design of the bike and visible to the rider and jealous onlookers. With the frame, fuel tank and other metal parts complete, it's then time to start thinking about building that all-important engine. Each engine is again built by hand by a small and dedicated team of engine builders. Here, the clutch pack of the bike is being built up.
Clutches are assembled here at Norton, so we'll buy all the component parts in. Clutch basket, hub, the plate, the springs, which will be hand riveted together and then assembled with the plates and the steels, all which need to be soaked in oil for 24 hours previous.
The building of the engine is another time-consuming process, with each engine taking around 4 hours to complete.
So the engine's a 961cc air-cooled parallel twin. It's a robust, torquey engine with about 80 horsepower, 80 newton meters of torque, Commando 961 range of bikes, about 125 miles an hour.
Whilst the engine builders are at work, the sub-assemblies of the bike are completed by a separate team. These sub-assembly parts are all built separately before they are fitted to the bike. Here, a number plate hanger that will fit to the back of the bike is being constructed. This number plate hanger also includes the lights for the bike's indicators. Whilst the rest of the bike sub-assemblies are being built up, the wheels are also being constructed. This is the lacing process, which is essentially fitting the spokes of the wheel to the rim. Once the spokes are fitted, they need to be fixed in place, which is completed using a torque wrench. This torque wrench ensures exactly the right tightness is applied to each nut. The wheels are then left to rest for 24 hours so that everything has time to settle into place. And they are then torqued up to optimum tightness once more. Now that we have our sub-assembly parts, engine and wheels, we can move on to the production stage of the bike build. At the production ramps, every element of the bike will come together, so that by the end of the line, we have a shiny new bike ready to hit the roads. At this station, the foot control arm is being fitted. The bike will continue to move down the line, with each station fitting different parts, all of which have been hand-built and pre-assembled on site. Here the airbox is being fitted. This vital bit of kit will pump air into the engine, keeping it firing and running smoothly at high speeds. Remember that fuel tank being welded? Well, now it can take pride of place on the bike. And with this fitted, along with spark plugs and other vital components, the bike is ready to be tested on the in-house dyno. Here the engineers can get the bike firing and check its gear changes, making sure that everything is working as it should be. And with that, the motorcycle is complete, ready to hit the roads and give petrol-fueled pleasure to its lucky owner.
People love motorbikes because they make no sense whatsoever. It's why you love motorcycles, isn't it? People don't like motorcycles, they love them.
Motorcycles, definitely one wicked invention. Nuclear power divides opinion. With the world living under the prospect of a nuclear Armageddon during the Cold War and the destructive power of the World War II ending US bombing of Japan, the word nuclear has many negative connotations. But the harnessing of atomic energy to create electricity has also demonstrated that if handled carefully, nuclear power can really be a wicked invention. So, it might be controversial, but what is nuclear power?
Well, nuclear power is harnessing the power of the atom. Essentially, there is a lot of power inside mass, and if you convert mass to energy, which is what Einstein formulated in his theory of E equals mc squared, the energy is proportional to the mass times the speed of light squared. So you don't need very much mass to generate a lot of energy if you can convert it from directly into energy.
Atoms are the smallest particle of a chemical element that can exist and are the basic building blocks of ordinary matter, as they can join together to form molecules, which in turn create most of the objects around you. What Einstein and others realized was that if you could split an atom, you could unleash an enormous amount of energy in proportion to its size. It might sound complex, but an atom splitting into smaller, lighter parts can happen naturally in certain materials, and this is called nuclear fission, and it releases energy in the form of radioactivity, which, depending on its type and strength, can be harmful to people. The heavy metal, uranium, possesses this quality, and it was its discovery which started the journey to nuclear power.
The discovery of radioactivity started with the discovery of uranium. Martin Klaproth discovered it in 1789. Didn't really understand quite what he had, but he knew that there was something special about it. And later on, you have people like Marie Curie who started to experiment with pitchblende, which is a mixture of uranium and radium, and they tried to separate out many isotopes and many elements, particularly, to work out what is this stuff, what is this radiation, what does it mean? They worked with radioactivity so much that the notebooks they used back from the 1900s are still too radioactive for anyone to go near, because at the time no one understood what radioactivity meant and what it would do to the human body.
Like other elements, uranium occurs in several slightly differing forms, known as isotopes. These isotopes differ from each other in the number of uncharged particles or neutrons in the nucleus. Natural uranium, as found in the Earth's crust, is a mixture largely of two isotopes. 99.3% is uranium-238, and the remaining 0.7% is uranium-235. The isotope uranium-235 is important because under certain conditions it can readily be split, yielding a lot of energy in an exothermic reaction that produces heat. It is therefore said to be fissile, and we use the expression nuclear fission.
In nuclear fission, what happens is typically uranium and a specific type of uranium called uranium-235, that breaks apart and releases 2 or 3 neutrons. These 2 or 3 neutrons can then cause another atom to release another 2 or 3, but only needs 1 neutron to do that. So each reaction in uranium can cause another reaction to happen.
The quest to harness this technique and create fast runaway reactions to power the devastating bombs that obliterated the Japanese cities of Hiroshima and Nagasaki in World War II led to a greater understanding of how nuclear fission could actually be controlled. After the war, scientists and engineers utilised far weaker nuclear fission to produce electricity. So, how do these power stations work?
A nuclear power station works by having radioactive material producing a chain reaction, but not a critical chain reaction. This is useful because if we take the neutrons that escape your radioactive system and they hit water, the water will eventually slow them down, and the heat that is from those neutrons, the energy from those neutrons, is converted into heat, which can start to boil the water into steam. Steam under pressure will now be then pushed through turbines. Those turbines can turn electromagnets. When they turn electromagnets, we have electricity. And that's how a nuclear power plant works.
This same power generating technique is also used to propel large submarines. With their nuclear generators only needing to be refueled once every 25 years, the only detail that stops them staying underwater for all that time is their cruise provisions. Typically, a nuclear submarine will carry enough supplies to maintain a 3-month stealthy presence beneath the waves. So, nuclear power is the perfect energy source then? Not quite. The radioactive waste generated by nuclear energy is dangerous and tricky to dispose of safely. The devastating environmental effects from accidents at atomic energy sites such as Chernobyl in the Ukraine and Fukushima in Japan have also stifled popular acceptance of nuclear energy. Are these accidents evidence of the danger of nuclear power, or are our fears misconceived?
People's fear of radioactivity comes from the atomic bomb. We actually encounter radiation all the time. Bananas are radioactive, very commonly known to be, and you can put a Geiger counter over those and they will light up, a Geiger counter. And that's because of the potassium-40 that is naturally radioactive. So nuclear radiation in nuclear power plants is designed to be kept as low as reasonably practicable, which means that in practice you'll often receive less nuclear radiation by being inside a nuclear power plant than by being outside of it.
No matter which side of the argument you sit on, there is no denying that nuclear power truly is a wicked invention. Nuclear fission is an exothermic reaction. Can we create our own exothermic reaction? We're going to need 2 rusty iron bars and some aluminium foil. We take one of the iron bars and carefully wrap a single layer of aluminium foil around its length, and we are ready to go. We take both bars and carefully strike the aluminium covered bar with the rusty one. After a few strikes, nothing much seems to be happening, but if we freeze frame the film, we can see some of the strikes are creating sparks. This is our very own exothermic reaction. In scientific terms, an exothermic reaction is a chemical reaction that releases energy by light or heat. In our case, we've actually created a thermite reaction. A thermite reaction is basically iron oxide, or as we know it, rust, reacting with aluminium to produce molten iron. Striking the two bars together creates a small area of heat. This heat, combined with the aluminium in the foil and the rust on the bars, produces aluminium oxide, elemental iron, and a large amount of heat and light. This action is similar to the process of igniting black gunpowder and is used in remote locations to produce white-hot molten iron for welding. Not a bad result for just knocking together a couple of rusty old bars. Can we create our own exothermic reaction? Yes, we can. Wicked challenge smashed. Ski boots are used by those of all ages and abilities, but just how were they introduced?
Ski boots are a relatively recent invention. Originally, for much of history, they were actually work boots tied to skis. They eventually evolved with straps tied to skis, and by 1840 you actually got a sort of heel plate to put the boot in.
Despite these heel plates, work boots were still worn while skiing. The heel plates would just attempt to keep the skier's feet in position. Up until around the 1870s, most of the shoes and boots were made by hand. It was around this time that we began to see customization of footwear to either fit a specific ski or customer.
Up until this time, the leather of the shoes was still easily affected, so within the snow, it would relax, it would lose its shape, it would get into the foot, so there were all these problems that needed to be solved. The first part of the revolution came in 1954, where Norton, he created the buckle that you recognise on ski boots today, because the buckle created a much firmer seal, it helps keep water out.
Not only would this buckle hold the skier's feet in a fixed position, the firm, snug fit meant that less snow and water could enter the boot, keeping the skier extra warm.
It was in 1962 that Bob Lang and Dave Lonsman created the vacuum-moulded plastic boot that we recognise today, and put together with the buckle that had come before it. The first sort of recognisable ski boot was in 1964.
This ski boot was so popular that in 1966, the Canadian ski team used the boots in various championships and races. Many saw the difference in performance, comfort and fit, which only increased the popularity of what was called the Lang boot. Today, ski boots are still worn on slopes around the world, but just how are they made? Salomon, named after its founder, George Salomon, produced ski boots right at the heart of the action in Annecy, located in the French Alps. They specialise in creating custom moulded and fitted ski boots and take great pride in providing athletes with these bespoke bits of kit that will help skiers tear up the snow.
At Salomon, we've been making boots since almost 40 years. The company was founded in 1947. In 1979, Salomon introduced the first alpine boot, which was a rear entry boot, quite revolutionary at that time on the market.
The production of a Salomon ski boot begins with market research that will help determine the customer's needs. This is conducted in the form of focus groups with various countries, dealers and athletes in order to determine the needs of each individual skier. This stage will reveal whether a particular boot should focus on being lightweight amongst other needs.
Here in the ANSI Design Center, we have the capability to start from scratch a new concept, which means to start from the market research and to go until a final product dedicated to the end consumer.
The correct last for the boot then must be defined. A last is essentially the foot shape that the whole boot is moulded around. Using this fancy bit of kit, a foot scan is taken off the athlete, and then all of the information recorded in the scan is uploaded to a database that can work out exactly the size and shape of the last that is required for each boot design.
In parallel, we're going to work on how do we create the new features and the new innovation. So we are working on the existing plastic parts, and we're going to try to rebuild a new boot with existing parts.
Next is the design creation stage. Using the defined last, a designer gets to work drawing out the boot's features and lines. They use mock-ups and trend boards for inspiration in order to best combine functionality with style. Using these designs, prototypes can then be created with old plastic components and handmade models. This stage is vital as it gives the designers a chance to transform their ideas and see them come to life. The prototypes allow them to evaluate the feasibility of each of their innovations.
As soon as we have some prototypes ready, we're going to go on snow to test them, to see if they are working well on the snow, which is at the end what we are looking for, and to make sure that, again, the innovation we want to bring is working on the field.
Once they are happy with their prototypes, the production of their new boot can really begin. Armed with the information from the design stage, moulds are created so that all of the plastic parts of the boot can be injection moulded. Injection moulding essentially forces melted plastic into a mould in order to accurately and consistently produce plastic parts. The shells of the boots are made using this injection moulding technique, as well as the cuff of the boot and even the sole. With the plastic parts complete, it is time for the liner of the boot to be created. The liner is there for comfort and to wrap the foot and hold it securely in place. This liner acts as a cushion from the shell, protecting feet from the cold in the meantime. The liner is built up in what is known as the soft pilot area, which is where all of the soft parts of the boot are worked on. The liner itself is composed of more than 230 pieces of foam, leather and textile. As well as providing comfort, this liner also plays an important part in the performance of the ski boot. It works closely with the plastic cuff of the boot to give just the right amount of flex for the user. Once the liner is complete, our boots are very nearly ready to hit the slopes. All that needs to be done now is to take these shiny new boots through their thorough testing procedure. In the testing lab, the boots are placed in a cold room that is set at the chilly temperature of -18 degrees centigrade. To put it into perspective, that's the temperature of your home freezer. In this cold room, the boots are put through their paces and tested for durability, breakage tolerance, and a whole host of other performance tests.
So we're going to have some machines that will reproduce a lifetime cycle. Like, for example, we're going to put a boot doing 35,000 cycles, which is something comparable to 5 years of use in normal conditions, to see if the rivets are good enough, if everything is good enough for 5 years.
And with the tests all passed, our boots are ready to be put into action on some of the world's biggest slopes and mountains. Snow boots, truly a wicked invention. So, there you have it, a dash through the hidden history, super science, and amazing manufacture of products that you use every day, but have never realised their amazing backgrounds. Motorbikes, nuclear power, and ski boots. All wicked inventions.